All right, kids, we're going to study collisions again today. We're looking at momentum and things like that. We're going to take a greater look at collisions, a deeper look. There's three broad categories here. Let's go through them one by one. The first one is called elastic collisions. How are they defined? Well, elastic collisions is where momentum is conserved. Momentum after the collision is equal to momentum before the collision. P prime is equal to P. Kinetic energy before the after the collision is equal to kinetic energy before the collision. It's conserved. Ek prime after the collision is equal to Ek. Where would you see something like this? Well, you would see something like this when molecules are bouncing into each other. For example, in the air, nitrogen molecules, oxygen molecules, carbon dioxide molecules all bouncing in off each other. This is basically what we're talking about right here. And I want to use this simulation to show you an elastic collision. I know it's an elastic collision because the elasticity, look at this word here, elasticity is 1, the maximum amount. So let's take a look at the red object, number one, the red glider. It's got a mass of 2 kilograms, a velocity of positive 5 meters per second, and with that, we could calculate its momentum, 10 kilogram meters per second, and its kinetic energy, 25 joules. Remember, energy is a scalar, momentum is a vector. Let's move on to glider number 2 here, the blue one, and it has a mass of 2 kilograms, a velocity of negative 1 meters per second. It's moving to the left, right? So we could use the mass and the velocity to calculate its momentum. There it is, negative 2 kilogram meters per second, a vector, and its kinetic energy, scalar, 1 joule. So if you were to add up the kinetic energies here, we would get 26 joules. And if we were to add up these momentums, 10 and then negative 2, we would get 8 kilogram meters per second. This is all before the collision. Let's have the collision. Here we go. And if you take a look at it now, the kinetic energy is still 26, 2, 25, it's 26, and the momentum is still 8. I have negative 2 and 10, but it's still 8. Both of these quantities have been conserved. All right, well, the next type of collision is what we call inelastic collisions. Inelastic collisions, and with inelastic collisions, the momentum is still conserved. Take a look at that. Okay, but the kinetic energy is no longer conserved. Where would you see something like that? What we call macroscopic collisions, macroscopic objects, everyday objects. If you're playing pool, billiards, and one ball knocks into the other, that would be an example of an inelastic collision. So I'm going to set up an inelastic collision here, and you notice the elasticity is now 0.5, and we notice everything stays the same. The kinetic energy is still 26 joules before the collision, just like before. The momentum is still 8 kilogram meters per second before the collision, but something very different is going to happen. Now let's observe. The momentum is conserved. Take a look at that. All right. You're to add these two up, but take a look at the kinetic energy. It has not been conserved at all. You only have 12 and a half joules, nowhere near what we had originally. This is an example of an inelastic collision. All right, and the last one is what we call completely inelastic collision. Look, the momentum is still conserved, but now the kinetic energy right after the collision is much less than the kinetic energy before the collisions, to the point where completely inelastic collisions are defined by the fact that the objects stick together. Let's take a look at one of those. So we're going to take a look at now at a completely inelastic collision. Look at the elasticity. Look at that. All the way to 0. It doesn't get much lower than that. It's impossible. All right. Everything's the same as we've always started these situations. The kinetic energy is 26 joules, momentum 8 kilogram meters per second. Let's see what happens. You already know they should stick together. Let's see. And they have stuck together. The momentum is conserved. Take a look at that. It's still positive 8 kilogram meters per second. Remember, it's a vector. Look at the kinetic energy, much less. We've taken a big drop. 4 and 4 is 8 joules. So we've taken a look at three different types of collisions, how they're defined mathematically, examples of each, objects that stick together. You know, a car hits a truck and they get all jumbled up together. The metal's bent and stuck together and they move forward as an object together. Billiard balls, playing pool, and molecular collisions like particles of the air. So we have examples, we saw it in the simulation, we have a mathematical definition for each of them, so we have all three types of collisions defined. All right, kids, let's do an example. Let's do an example of a head-on collision in one dimension. Let's say that it is an elastic collision, so momentum and kinetic energy are conserved. And here's the situation. We have an object, mass 1. It's moving to the right with velocity v1, and it's going to hit an object m2, and its velocity before this collision is 0. It's just sitting there. Okay, just sitting there waiting to be hit. And let's make it even simpler. Let's make it even simpler. Let's say that the mass of the first object is equal to the mass of the second object. So let's just call that mass m. We don't use the 1 or 2. They're both the same mass. How would you go about trying to solve for what the velocity of the first object is after the collision and what the velocity of the second object is after the collision? Well, you would use the power of the definition of the elastic collision. We would take advantage of the fact that the kinetic energy is conserved, and we would take advantage of the fact that the momentum is conserved. So let's work through these. Kinetic energy after the collision is equal to kinetic energy before the collision. This is equal to the kinetic energy of the first object after the collision plus the kinetic energy of the second object after the collision. You need the total kinetic energy of the objects after the collision. On this side, kinetic energy before the collision is equal to the kinetic energy of the first object before the collision, and to that we will add the kinetic energy of the second object before the collision. It has to be the total. Luckily for us, the second object was not moving, so we can just ignore that. 0. Now we're going to write out the equation, the expression for kinetic energies. So we do that. We know that kinetic energy is half the mass times the speed of the object. So look, I've replaced each one with the appropriate kinetic energy. There you have it, right? Half the mass times the velocity of the first object after the collision squared, v1 prime, velocity of the first object, prime meaning after the collision squared, v2 prime squared, velocity of the second object after the collision squared, v1 squared, velocity of the first object, there's no prime, it means before the collision, squared. Luckily for us, there's a half in each term, so we can divide it out. And there's a mass, which is the same for all of them in each term, so we can divide it out. And we can create equation A, which is the speed of the first object after the collision squared plus the speed of the second object after the collision squared is equal to the speed of the first object before the collision squared. Equation A. So we've taken advantage of this part of kinetic energy definition in what is an elastic collision. Now let's go over to here where we're taking advantage of the fact that in an elastic collision, momentum is also conserved. So we have P prime, momentum after the collision, is equal to P, momentum before the collision. Well, P prime has to equal the total momentum after the collision. So it would equal P1 prime, the momentum of the first object after the collision prime, plus P2 prime, the momentum of the second object after the collision prime, is equal to, on this side, the total momentum before the collision, which would be the total momentum of object 1 plus the total momentum of object 2. Well, luckily for us, object 2 wasn't moving, so that whole term is gone, 0. Now we're going to write the expressions, the equations for momentum. Remember, momentum is defined as multiplying the mass times the velocity here, but we're only going to look at the magnitude part. So we're going to drop the vector notation. We're only looking at magnitude, and we'll say that momentum here is equal to mass times v1 prime plus momentum of the second object after the collision, mass v2 prime, and momentum of the first object before the collision, mass v1. Now, luckily for us, the masses all cancel out, and that gives us v1 prime plus v2 prime is equal to v1, and you'll see later why I'm doing this, but I'm going to rearrange this for mathematical simplicity and say that v1 prime is equal to v1 minus v2 prime. I brought v2 prime over to the other side. I brought v2 prime over to the other side, and I made it negative. And I'm going to call this equation B. And now we're going to substitute equation B into equation A. So where the v2 prime is, see that v2 prime is right there? Ooh, made a mistake, sorry. v1 prime, see it right there? v1 prime. I'm going to replace v1 prime with an expression for v1 prime. There it is. I'm going to replace it. So let's do this. What do we got in equation A? v1 squared. Okay, v1 squared. What's v1 squared equal to? Well, it's equal to v1 prime squared. Well, I'm going to replace it with v1 minus v2 prime because I know they're equal. All squared. And then plus v2 prime, it just stays along for the ride. So I've made this substitution right there. Then what do? Well, then we have some fun. We use my friend and yours, FOIL. First, outside, inside, last. And that's what gives us this trinomial right here. First, outside, inside, last gives us this trinomial. v1 squared minus 2v1 v2 prime plus v2 prime squared, and this plus v2 prime squared stays right there. That stays. And the v1 squared on the left side of the equation also stays, and the equal sign stays. Let's continue. We notice that we can collect these terms here. They're the same. v2 prime squared and another v2 prime squared, so I can collect them. And I get 2 times v2 prime squared. There you have it. And all the other terms are maintained. What's next? Well, look, I've got a v1 squared on the left-hand side and a v1 squared on the right-hand side. I can bring it over. This one right here that's on the right-hand side, I bring it over, becomes negative, and then they're the same term. They're subtracting from each other. You're left with 0. You're left with 0. So now I have 0 is equal to negative 2 v1 v2 prime plus 2 v2 prime squared. And lucky for us, we can divide through by 2, and we do that. And the 2's are gone. We divide the whole equation by 2, and we're left with this expression right here. We're left with this expression right here. Negative v1 times v2 prime plus v2 prime squared. What are we going to do next? Well, we notice we can factor out a v2 prime. So I'm going to factor out a v2 prime out of each one of them, and I'm left with a negative v1 here and a positive v2 prime right there. And they both have to equal 0. All right? So the only way you can get 0 on this side is if v2 prime is 0, or if what in the bracket is 0. 0 is equal to negative v1 plus v2 prime. Well, v2 prime equals 0 would be telling you that the velocity of the second object after the collision is 0. That's not possible. It's just been hit by the first object. So this is telling you there's no collision. This is an extraneous route. It's not possible. But this one is possible. This one is very much possible, that v2 prime is equal to v1. So what it's basically telling you is that the second object after the collision ends up having the velocity of the first object before the collision. Now we're going to use this and we're going to substitute it into equation B. And when we do that, we get V1 prime is equal to V1 minus V2 prime. But look what V2 prime is. Look what we just found V2 prime to be, V1. So I do the substituting. V1 minus V1, 0. Meaning V1 prime is 0. Meaning the velocity of the first object after the collision prime is equal to 0. It stops. Let's see if this actually happens. All right, I've got this set up just like our question. Number 2 is not moving. They're the same mass. Number 1 is moving. Let's do it. Oop, I didn't do that right. Let me fix that one. We'll set it up. I said the second one was not moving. I made a little boo-boo there. Let me fix that. Here we go. This should be much better. There, much better. And as we saw in the mathematics, the first object comes to a halt and the second object takes on the velocity of the first object. The first object was moving at 5. The second object was moving at 0, but now look, they've switched. Just like the mathematics told us. All right, last example for today. We have a nitrogen molecule. We're going to say its mass is Mn, and it's going to have an elastic collision with an oxygen molecule, mass MO. Now, the oxygen molecule before the collision is not moving. The nitrogen molecule is moving. We're going to say it has a speed Vn, and they're going to have an elastic collision, meaning that the kinetic energy after the collision must equal the kinetic energy before the collision. That's very important. And the momentum is also conserved. Momentum after the collision is equal to momentum before the collision. All right, we're back. We're going to substitute in the values just like we did last time. There you have it. The only problem now is that the masses are not the same. The masses are not the same. So I'm still going to get rid of the halves by dividing through. But now I'm going to divide each term by mass of nitrogen. So it eliminates here. It eliminates here because you're dividing through. It leaves you with a 1. But here it leaves us with a quotient. Mass of the oxygen divided by mass of the nitrogen. So I divided each term by that, and I'm going to call this equation A. Now I'm going to go over to the momentum side, just like we did in the last equation. Set it up. Momentum is conserved. I've set it up right here. I'm going to now divide each term by mass of the nitrogen molecule. So here it divides through, leaves us a 1. Here it divides through, leaves us a 1. But here it leaves us a fraction. Here it leaves us a fraction. Now I'm going to take this term in the middle, bring it to the other side, make it negative, and that will be equation B. That will be equation B. And just like in the previous equation, I'm going to substitute B into A. I'm going to substitute B into A. So here is equation A. Here's equation A. Here's my Vn prime. Here's my Vn prime. I'm going to replace Vn prime with this term right here in B. And that's what I've done. I've put it in. This term stays the same. This term stays the same. Now I'm going to use my friend and yours. I'm going to FOIL this binomial to create this 1, 2, 3 trinomial right there. This binomial through FOIL creates the trinomial right there. You can figure that out on your own. This term right here remains. I'm just going to recopy it. And this term right here remains. I'm just going to copy it. Now we have to be observant and we have to realize that we have a velocity n squared on each side. Look, Vn squared here and Vn squared there. So I'm going to bring this over to the other side. It will become negative, and when they subtract, we will have 0. And the other terms remain. This term remains, this term remains, and this term remains. Okay, let's continue. All right, let's continue and see how we get to this next line here. How do we get to the next line? Well, we do that by multiplying each term here. We do that by multiplying each term here by mass nitrogen all over mass oxygen. So when you multiply that into here, it eliminates the fraction. And we only have negative 2 velocity nitrogen molecule before the collision, velocity oxygen molecule after the collision. When you multiply this mass nitrogen over mass oxygen into here, it eliminates the square. So we only have mass oxygen over mass nitrogen. And when we multiply mass nitrogen over mass oxygen, we multiply it into here, and it eliminates this fraction. So we're left with this term right here. What you now have to recognize is that you can do some factoring between these two terms because they're both based upon velocity of oxygen after the collision squared. Velocity of oxygen after the collision squared. So I'm going to factor that out. There it is. I factored it out. And what am I left with? I'm left with this fraction, mass of oxygen over mass of nitrogen. And here I'm left with a 1 because I have to have a term there if I factor out. And it leaves us with this line right here. Well, what are we going to do next? Well, we're going to take a look at these two terms here. We're going to take a look at these two terms here, and we're going to factor out a velocity of oxygen after the collision out of both of them. So I'm factoring this V naught prime out, and I'm left with negative 2 velocity of nitrogen. Over here, I have velocity of oxygen after the collision squared. If I factor one of them out, the squared is removed, and I have velocity of the oxygen after the collision. And I just have that. It's no longer a squared term, and I still have the term in the bracket, and it's still equal to 0. Now, we're left with a similar situation to the previous example. The only way this product, this multiplied by what's in the bracket, the only way it can equal 0 is if V naught, V velocity of the oxygen after the collision, so V oxygen prime, this can equal 0, or what is in the bracket can equal 0. That's the only way we're going to get a 0 on the right-hand side. Well, velocity of the oxygen after the collision equal to 0, that makes no sense because the oxygen molecule was sitting there and it was hit and there was a collision, so it would move. So this is an extraneous root. We're not going to accept that. But we can accept that what is in the bracket is equal to 0. Let's work with that then. So here it is. What's in the bracket is equal to 0. What's in the bracket is equal to 0. So what I'm now going to do is I'm going to take this term right here, velocity oxygen after the collision times by what's in the bracket here, and I'm going to bring this whole thing over to here, and it will become negative. There, it's negative now. All right? And I'm going to divide it through so that I can isolate for velocity of oxygen after the collision. There, I've isolated for it. Aha. I now have a viable solution. I now have an expression that will actually give me a value for velocity of the oxygen molecule after the collision. This makes sense. I can then use this to find the velocity of the nitrogen molecule after the collision. That goes back into equation B. Here's equation B. Here's equation B. And I can then say, look, here's a V naught prime there. See that? V naught prime? But I know what V naught prime is. There it is. So I'm going to plug it into there, and now I have an expression for velocity of the nitrogen molecule after the collision. And we're done. We're done our two examples. A lot of math, a lot of math. Take your time going through it. Be patient with yourself. Pause the video, rewind it, make sure you get it. I know it's hard work, but school's on and you all want to go to university. It's not easier there, so work hard. So we got here a simulation of the last example we did. All right, because this would be the nitrogen molecule. It's heavier than the oxygen molecule. You see that? This one is not moving. Initial velocity is 0, just like our oxygen molecule was not moving. Here's what's representing a nitrogen molecule. It was moving. So let's do it. And there you have it. This one slows down. This one speeds up. The momentum is uh, conserved here. Take a look at that. The momentum is conserved here. And the kinetic energy is also conserved. If you were to add these up, you would see it is what we have to begin with. All right. You would see it is what we have to begin with. There you have it. Enjoy your day.